Okay, so we're talking about these three laws that were mentioned in our objectives, and we're going to see how that applies to chemical reactions, where we make one chemical or more chemicals react with one another, and there are going to be transformations that happen in those. Okay, so the first law is the law of conservation of mass. It says that mass cannot be created or destroyed. So when we carry on a chemical reaction, all the mass I start with, I have to end with. I'm not going to create any new matter, and I'm not going to destroy any matter that I started with. All the matter I started with needs to be accounted for at the end. So that's what we mean by the conservation of mass. So every ordinary chemical or physical change, this is going to be true of. Just because I melted ice and made it liquid water doesn't mean I've lost any mass. All the water's there that was originally as ice, or if I go the other way around. Okay, the next one is the law of definite proportions. Okay, now this has to do, here we're talking about a single chemical compound. Just take water as an example. Okay, a chemical compound contains the same elements. Is water always made of hydrogen and oxygen?
Yeah.
Yes, okay. It's always made, and exactly in the same proportions by mass. Okay, the mass of hydrogen plus the mass of oxygen makes up the mass of a water molecule, and it's always the same proportion by mass, regardless of the size of the sample, whether I have a little thimble full or I have a bathtub full of water, the proportions of how you make water is always the same proportion by mass, never any different. Okay? Now, the law of multiple proportions is talking about more than one compound. Okay? Multiple. And if you have two or more compounds that are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. I think that we need to look at, like if we have water, and then we have hydrogen peroxide. Okay, if you look at, now let's look at what we have up here again. We have two more different compounds. This is two, we could have more, but let's just take two for right now. Composed of the same two elements. In our example here, it's hydrogen and oxygen, made up of the same two elements, and the ratio of the masses of the second element, this is oxygen in this case, combined with a certain mass of the first. They have the same mass of the first, right? They're both two hydrogens, which works out kind of nice on this one. With a certain mass of the first element is always a ratio of small whole numbers. This is a ratio of 1 to 2. Okay? It won't be fractional. You know, like 1.6 to 3.8 or something like that. It'll be, as it says there, small whole numbers. Okay, so this is the law of conservation of masses of different examples of chemical reactions. Like if I take a hydrogen gas and I burn it in the proper amount of oxygen, it will burn and form water molecules. And the next one is if I have sulfur, if I burn sulfur and oxygen, it forms sulfur dioxide. Sulfur dioxide really burns in the nose because it wants to combine with water vapor or water moisture. It's in your nose, and that's another chemical reaction, and it actually forms sulfuric acid. That's why it burns in your nose, because it's actually becoming an acid in your nose. The next one is phosphorus pentachloride will decompose into phosphorus trichloride and a chlorine molecule, so that was another. But what I start with, I have to end up with for the conservation of mass. Here is an example that I often give for this. Let's say, to be able to show this to be true, let's start off with a log, or not a log, but a small piece of wood. We're going to burn it, okay? And we put it in this closed container, and then we have maybe a way of igniting it, maybe using like an igniter that I don't know if any of you have ever shot off model rockets, you know, that little igniter that you have. Let's say we have something similar to that to get the log burning. But the log, and we pumped all the air out of it first in this chamber where we have the log. We pumped all of it out, and we're adding oxygen to the container from, let's say, an oxygen bottle, okay? And we've weighed the log, we've weighed the oxygen bottle before we start, okay? Now, as the log burns, what are things that we know that are given off? Okay, well, we know that we're going to get some water vapor. So, let's say that comes out of the chimney or whatever you want to say, we collect all that, then we run it through a cooler that condenses it into liquid water, and so we'll collect our liquid water. It'll also give off carbon dioxide, and we have some chemicals that will absorb carbon dioxide. We know that. It's if you've ever watched the movie Apollo 13, they used chemicals to absorb carbon dioxide. They call it their CO2 scrubber is what I think they called it in the movie. But it takes out the carbon dioxide that the astronauts were breathing so that the air didn't keep getting filled with carbon dioxide until they finally passed out. Okay, so, but we'll have this chemical, so we weigh this chemical first before it starts absorbing carbon dioxide, and we'll weigh it at the end. There might be a little bit of ash, so we'll have maybe a filter that keeps the ash from escaping. So we weighed the filter before, we weighed it after. You know, we've done everything to collect all the things that are given off when this log burns, okay? So we'll weigh the amount of water. We'll weigh the amount of weight gained by my CO2 scrubber. We will weigh the amount of soot that's given off. And we'll weigh the ash that's left over when it's done burning. Then we'll weigh the difference in the oxygen bottle. How much oxygen did it actually use? Then we weighed the log. Well, the log plus the oxygen weight will be exactly the weight of all these others added together. That's what it's saying. That all the mass I start with is there when it's finished burning or whatever chemical reaction it happens to be. Okay? Law of multiple proportions. We had water and hydrogen peroxide. Their example is nitrogen monoxide and nitrogen trioxide. We could have used carbon dioxide and carbon monoxide as well. Could have used those two. It's the same two elements. And now where are they getting these mass numbers? Well, they're getting those from the periodic table. Notice that they have nitrogen is 14. Well, on my periodic table, this number right here on the periodic table is where I'm getting the 14 from. And the oxygen, I'm getting that from right here. It's 15.9994, which is really close to 16. I'll say this now, we'll say it a couple times here at the beginning of how we're going to do it. The periodic table has those numbers that are in the upper right-hand corner. Those are represents relative mass. And some of them have way more digits than others. What we're going to do is we're going to round every one of those masses off when we use them to 2 places past the decimal. So if some of them have more than that, we just round off to 2. So 15.9994 rounds off to 16.00. Okay, and that's where they get that. So if you, the ratio of nitrogen to oxygen in both of those, the top one is 16 to 14, the other one is 32 to 14. So the ratio of the masses of oxygen is 1 to 2 in that one. Now, compounds contain atoms in a whole number ratio. This idea then has behind it, when you say whole number ratio, is that you can't have a piece of an atom. When, in chemical reactions, you either take the whole atom or not at all. Okay? There's no in between. Like I need a half an atom, I can't give you a half an atom. You either take all of it or you take none of it. That's your only choices. There's a guy by the name of John Dalton. If you read anything in your textbook, it might give you a little bit of history of him. He was an English school teacher. Now, back then, even today we have people who teach that have other interests, they're experimenting and learning more. And one of his happened to be chemistry. He was learning, how do substances react with each other? Remember, they didn't really know much about atoms at all. So he's making some discoveries and coming up with some conclusions. Now, his theory said that all matter is composed of extremely small particles called atoms. Atoms of an element are identical in size, mass, and other properties. Atoms of different elements are different in size, mass, and other properties. So this is what he's saying about the atoms of an element, okay? That if you have an atom of oxygen, they're all identical in size, mass, and the properties that they have. Davis?
Why do you think he called them atoms? Because, assumably he just made it up.
Yeah, there's, in part of this history, there were people that already introduced the idea of particles, and I think we give credit to a guy by the name of Democritus for coining the word atom. It was actually, I think, in Greek or Latin. I think it was atomos, A-T-O-M-O-S or something like that. So in other words, that name had been floating around before, right? Atoms cannot be subdivided, created, or destroyed. You can't make atoms, you can't destroy atoms, and you can't subdivide them, chop them in half or chop them in a fourth. Okay? So this is in chemical reactions. Now, we're not talking here about atomic accelerators, which came along a lot later, back in the 1900s is when they came around. He's back in the, 1600s? I always forget when he lived, something like that. Okay, those are atoms of different elements combined in a simple whole number ratio to form chemical compounds. So when you take hydrogen and oxygen and put them together, it's always like 2 to 1. They're whole number ratios, not decimal numbers or fractions or something like that. In chemical reactions, atoms are combined, separated, or rearranged. So when a chemical reaction takes place, you have atoms that are just separating from each other and they're regrouping, okay? But all the atoms are there at the end. They just maybe are now in different groups than they started out with. Okay, so they're just combined. They'll separate from each other and rearrange in new patterns. Now, Dalton's atomic theory explains the law of conservation of mass through the concept that chemical reactions involve merely the combination, separation, and rearrangement of atoms. So when you have the conservation of mass, remember we said that the amount of matter I start with is the amount I have at the end? His explanation from one of his theories, or points of his theories, is that the last part there, the combination, separation, and rearrangement of atoms. That's all you're doing when you have a chemical reaction. When this log burns, all you're doing is taking the atoms that make up the log, you're separating them and rearranging them to make things like water, carbon dioxide, and maybe pieces that make up the ash. I guess we talked about soot too, didn't we? Which is probably like little particles of carbon typically is what soot is. But in other words, all the atoms that are there, they were arranged one way in the log and in oxygen molecules. And when I'm done, I have the same atoms, just arranged in different groups. So I didn't create any atoms, I didn't lose any atoms, they're just all there. They separated and recombined in different ways. Okay, it also explains the other laws, and they don't. Okay, why doesn't it go? Okay. Maybe that has something to do with it. I don't know. Sometimes other things pop up, and it gets busy doing. There we go. But I wanted to go back and pick up one more thing here. Dalton's atomic theory also explains the multiple proportions and the definite proportions. The reason why, like for instance, water always has a definite proportion, because you're always taking whole number of atoms. It's always 2 atoms of hydrogen and 1 atom of oxygen. You're not taking fractions to put them together. They're always whole pieces, so there will be whole numbers. And the multiple proportions is kind of a similar idea. You're taking whole atoms. It's just that sometimes they, like for instance with hydrogen, 2 hydrogens can sometimes bond with only 1 oxygen, but sometimes they can bind with 2 oxygens, and you get something else. Now, atoms can be subdivided into smaller particles, okay? Now, what are the smaller particles that make up an atom that you already know? Yes.
Electron.
Electrons,
Proton.
protons,
Neutron.
neutrons, good, okay? So we know that, for instance, that atoms can be subdivided. So that's one piece of Dalton's law that said that atoms cannot be subdivided. You know, that is, we've actually shown to be not true today, okay? So out of Dalton's laws, I think he had like 5 different things. This is one of them that has been shown that it's not true. Okay, atoms are divisible into smaller particles. We have discovered that today. It doesn't typically happen in a chemical reaction, though. Okay, so we don't have to worry about it this year that atoms are going to subdivide. Okay, a given element of atoms can have different masses. Now, does anybody remember from physical science what could possibly make an atom of an element have a different mass than another atom of that same element? What was the part that could be different?
Doesn't it have to do with our isotopes?
Okay, yeah. So why can you have different isotopes? Okay, that's now you're giving a name to what I was talking about. They're called isotopes. How can we have more than one isotope of an element? What's the part that's different? So Ben named the 3 parts: electrons, protons, neutrons, the order that he gave them in. Which of those can be different and give it a different mass?
Electrons?
Okay, electrons are extremely small, so we won't use electrons. Anybody else? Okay, protons, it can't be different to that because what element it is determined by the proton. So, but we're talking about the same element, so it can't be electrons because they're too small. Can't be protons because then I have a different element. So we're down to neutrons, okay? So the different isotopes that Laura's talking about have different numbers of neutrons. Okay, he said they all had the same mass. Now we know they're not exactly the same mass because there's some that have different masses because they have different numbers of neutrons. Protons the same, electrons the same, but neutrons are different. Okay, so that's another thing that we've discovered out of his 5 ideas that we've had to modify. That atoms are divisible into smaller particles, that atoms of an element do have different masses, Now, but what of Dalton's theories have not changed? Okay? All matter still is composed of atoms. He believed that back then, we still believe that. All matter is made out of atoms. Okay? Atoms of any element differ in properties from atoms of other elements. Yep, we still. In fact, we have them grouped in columns because they have similar properties. So we still agree with him on that concept. It's kind of hard to imagine that somebody who thought of this that many hundreds of years ago, he was right on. He wasn't on in everything. You know, we found a couple things we had to modify, but I mean, just to think that long ago, and didn't have all the fancy stuff that we have today to study this, was able still to figure these things out. Okay, so those are some things that haven't changed. Okay. Okay, so we're going to stop right there. It's kind of early, I know, but we're going to stop at that point. Normally, we would be handing back a test and talking about that, so we don't have a test to hand back. We have extra time. Does everyone have a note packet?
No.
Somebody didn't pick one up yesterday? There you go. Davis?
Thank you.
Oh, you want to turn it on? Push the button.
Hi, Angela.